Hi everyone, and welcome to this new class in aerodynamics and specifically the description of lift and drag. So here we have what would be the schematic forces of lift and drag and how they are related to velocity. So lift and drag depend on the cruising velocity of the aircraft. Depending on the velocity, we will have more lift or less lift, and more drag or less drag. Drag has the same direction, the components, as the velocity, whereas lift is actually perpendicular to the velocity. This is quite interesting because, as you can see, depending on the design of the airfoil, we will be able to transform this velocity into lift, and even if we don't want to, we will also have some drag. So you can see that this design of the airfoil will actually enable us to optimize the relation between the lift and drag. So airfoils, which are this over here, on the aircraft, is actually the cross section of the wing, right? Depending on our requirements, our lift requirements and drag, and also we will be defining some kind of airfoil or another. There's actually a lot of work in the aerospace industry in designing and optimizing exactly the geometry of these airfoils. So some airfoil parameters which are interesting. First of all, the chord line. The chord line is the distance, the line which relates the leading edge, and the trailing edge of this airfoil. So in this case it would be something like this point over here, the leading edge, and the trailing edge over here. So you just relate the 2 points and you draw a line and you have the chord line. You also have the camber line, which is this over here, in blue. This camber line actually defines the center with respect to the lower surface and the upper surface. So this line is the distribution, of the same distance, perpendicular distance, respect to the lower surface and the upper surface. So it's just the main line or the average line of thickness. Right, so as you can see, this line is just halfway to the upper surface and lower surface in all points. Right. Then you have the thickness also. The thickness just defines the thickness of the airfoil. By definition, as you can imagine. This point, for instance, is the maximum thickness. It's also interesting to note this. This length over here is actually the maximum camber, which is the maximum distance between the camber line and the chord line, alright? And also you have the chord, So this chord line is actually known as a distance, and this distance is just the chord, So you would have an interesting geometrical parameter, which is the chord, which is this distance, and all the other parameters are just defined in order to optimize the ratio between lift and drag. Another interesting thing to note is the angle of attack. Angle of attack is the angle relation between the relative wind, which is experiencing the aircraft, and the line, the chord line. So this chord line will define a specific orientation, right? And the relative wind with respect to that is just the angle of attack. This angle of attack is very famously known, and it is very important to design the airfoil in itself, right? So you can imagine that depending on the orientation of the aircraft, you will have a specific angle of attack or another one. Now let's see some more theoretical basis respect to the how are we creating lift, because we have a specific airfoil. So what is the configuration of the airfoil, what is the geometry of the airfoil, and how is it related to creating lift, right? So most of the time in aeronautical engineering classes, and specifically in aerodynamics, there's a lot of mathematics involved, and what we do is actually compute the difference in pressure, between the lower part of the lower surface, and the upper surface of the airfoil. And we usually get something like this. This means that because we have a certain angle of attack, usually, as by definition, then the wind will actually kind of collide with the lower part of the airfoil, okay, and thus some wind will be pointed downwards like this, okay. So you can imagine that there's a difference in the direction of the wind, okay, and this difference, right, implies that because the wind is actually blown away downwards, it will imply that there's a force, a positive force, okay, and an upwards force, a lifting force, okay, on the wing itself, right? So this would be the best, or the first definition at least, of what lift is. Now, as you can imagine, it's quite intuitive, okay? Imagine that you have just a plane, some kind of plane surface, any kind of plane surface, and you can imagine that depending on the angle of attack, okay, so if we increase this angle of attack, we will actually be able to increase the lift, okay? This is the coefficient of lift, it's just related to the lift, okay? I'll just explain this a bit later, but the idea is that if the coefficient of lift increases, the lift increases, okay? So this would be how you define lift, because there's some angle of attack, okay? So it's quite intuitive to understand that an angle of attack implies lift. Right. What else? The other theoretical approach is actually the Bernoulli effect, okay, which basically relates pressure and velocity. Now, Bernoulli effect is quite interesting and describes quite well why a specific geometry of the airfoil will actually imply more or less lift, okay? So imagine that you have a specific geometry which is able to change the velocity of the particles on top and on the lower part, right? So if you can see this, it's quite interesting to I will try to explain this as well as I can. Velocity on the top will actually be higher, okay, because we have this configuration, because we have this geometry. So it's kind of, there's a lot of mathematics on the background, but they kind of derive that this is the best geometry, okay, in general terms, to create the difference in velocity from the top and the bottom, okay. So if we have difference in velocity on the top of the airfoil and on the bottom, velocity and pressure are related, okay? And pressure is just the amount of force divided by the surface. So you can imagine that if the pressure is high, it implies a high force, right? A high force acting on the airfoil. And if it's, of course, if the pressure is lower, then it implies that that there will be probably a pull, okay, a push of the airfoil towards upwards, okay. So the idea is this: in the top we have high velocity, on the bottom we have low velocity. So low velocity on the bottom implies high pressure, okay, because all of this parameter, which is the dynamic pressure and the static pressure, should actually be constant, okay. So the idea is high velocity, low pressure, okay? They are inversely related. High pressure, low velocity, right? So because this has to be constant, if all of this is very high, then this has to be small, okay? I'm not gonna get into the mathematics, but that's the idea. High velocity, low pressure. So in this case we have high velocity, so we have low pressure. And in this case we have little velocity, so we have higher pressure. And this is just represented like this, okay? Now, the idea here is that we still have some pressure, okay, acting here. But because we have more pressure on the bottom, there will be a net force, okay, of the airfoil on upwards, okay? So the Bernoulli effect is just that, the relation between velocity and pressure, and how that implies a difference in pressure, okay, on the airfoil, because the pressure on the upper part is lower than the lower part, and therefore you have a net force, okay? And this net force is the lift. Right, so this is kind of what you need to know, angle of attack and Bernoulli effect. Okay, now let's just discuss a bit of the relation between lift and the different parameters. Okay, so for the description of lift and for the description of drag, you need this letter, which is the rho, okay, this is density. you need a velocity, the surface, and a coefficient of lift. So, first of all, you would need a wind tunnel, for instance, and you would define some kind of geometry, okay, for the airfoil, and you would test it with different angle of attacks. If you do this, you will get this kind of curve relating the coefficient of lift, okay, and the angle of attack, right? So you can see that the lift is a function of the angle of attack because the coefficient of lift is actually a function of angle of attack, okay? However, the lift also depends on the density, the velocity, and the surface. So velocity is just the relative wind with respect to the aircraft. The density is actually the amount of particles that there are in the air surrounding the aircraft, right? So, of course, if you have a if there's a lot of particles, you would have more lift, right? Because there's more particles colliding with the airfoil. And if you have low amount of particles, then there's less lift, right? So you can imagine that if you're flying at very low altitudes, the density will be high, and therefore the lift will be high. But if you're flying, say, at 35,000 feet, for instance, the density is really smaller, and therefore the amount of lift would be smaller. And because you need always to maintain the same amount of lift, more or less, okay, it would imply either speeding up the aircraft or changing the angle of attack, okay, to get more coefficient of lift, for instance. So the idea is that you have to keep the lift equal to the weight on all the cruising operation, okay, and the drag equal to the thrust, right? So it's just you have to design the aircraft in such a way that it is easy to increase a bit the angle of attack, and you have more lift, okay, or you play with the velocity, or with a surface you cannot play, right? Because the surface would be fixed initially. Let me just explain this also. The surface is the amount of surface that we have with this airfoil, but also due to the wing, okay? So the surface would be the airfoil, the chord, okay, the chord line, this distance, multiplied by the wing span, okay, the wing length, right? So you multiply these two coefficients and you get a surface, an equivalent surface, okay? Right, so this is how you define the lift and the drag. Another interesting thing to know is that the coefficient of lift is just a coefficient. It just relates the geometry, okay, with the equation, basically. And you have this coefficient of lift, which usually here is 0, okay, minus 5 degrees is 0, and you know, at some other points is 1.5, 1.6, okay? But usually you will have a coefficient of lift probably around 0.5 and 1.5, okay, depending on the configuration and you know, the conditions of the cruise flight, okay? But just around there, which you can understand is related to 5, you know, 5 degrees is quite typical, 5 degrees angle of attack for a normal cruising flight, okay? What else? Yeah, it's quite interesting to note that you may have seen that this curve is kind of linear, okay? Not exactly linear, but kind of linear. From low degrees, minus 5 degrees, for instance, something like that, to high degrees, 10, 12 degrees, okay, are kind of acceptable. More degrees, you're probably going to have problems, okay? Because this part over here, this is known as stall. We'll explain this better in other videos, but the idea is that if you continue to increase the angle of attack, then you would actually have stall, which implies that the aircraft, okay, because if you have a very high angle of attack, you would have high turbulence on this part of the airfoil, and therefore you would not be able to transform the velocity into the difference in pressure, and following Bernoulli, right? And therefore you would have a decrease in the lift, okay? And actually it's if you are flying in these conditions, you will lose all stabilization, all control of your aircraft. So it's absolutely essential to fly in some range which is linear, okay, or some range which is easily controlled. What else? Yeah, I wanted to point out also that as I mentioned, lift is around 0.5, 1.5, okay? Drag, the coefficient of drag, I haven't drawn here, I will explain later, is around 10 times less than the lift, okay? So if lift is around 0.5 to 1.5, drag would be 0.05 or 0.15, okay, something like that. So a magnitude of 10 is the difference between the lift and the drag, okay? Not sure if I'm leaving anything. Otherwise, this is all for this video, okay? I will upload more content on aerodynamics and also the other topics as soon as I can. So, see you in next class.